Chapter 9 is about sequences and series. Chapter 10 is about a special kind of series called Taylor series. Very special and important kind of series, more related to functions. Here in chapter 9, the sequences and series we deal with are more numerical, you might say, though there's still functions going on. You've learned about sequences, lists of numbers, oftentimes with patterns, since you were pretty young, probably. 3rd, 4th, 5th grade. What's the simplest sequence? How about this one? 1, 2, 3, 4, 5, 6, blah, blah, blah. The counting numbers. That's a sequence. It's got different names. Counting numbers, whole numbers, natural numbers, positive integers. All those words mean the exact same thing, the exact same sequence. Technically, this as a sequence is different than this as a set, because sequence means they go in order. With sets, yes, you can write the numbers in the same order, but I could rewrite the numbers in a different order and it would still be the same set. With sets, you don't really care about the order, though sometimes it's convenient to write them in a certain order. With sequences, you care about the ordering. This is called the first term, that's called the second term, this is called the third term, etc. And we have special notation. S sub 1 represents the first term, S sub 2 represents the second term, S sub 3 represents the third term, etc. We use subscript notation to identify the term. At first, we start with the first term here, but then maybe starting next week, we'll realize that sometimes we may want to start with, say, the 0th term. We might want an S sub 0. And there's actually nothing stopping us from starting at the negative 17th term if we want. Kind of crazy, but there's technically nothing stopping us from doing that. Keep it simple today. If we start with the first term, there is a direct formula for S sub n. It equals n. Because S sub 1 equals 1, S sub 2 equals 2, S sub 3 equals 3, etc. A direct formula. Why call this a direct formula instead of just formula? Why use the word direct? The reason is because there's going to be indirect formulas as well. Just like with functions, sometimes there are explicit functions where y is solved for, and there are implicit functions where y is not solved for. So with sequences, there are direct formulas where Sn has a simple formula, you might say, involving n, and indirect formulas where Sn might depend on S sub n minus 1, or maybe even S sub n minus 2, or maybe even both, or maybe even other strange things. It's assumed that n is a positive integer here. N is 1, 2, 3, 4, etc. It is good to specify the domain here. And in fact, it's not a bad idea to call that a domain. This is really a function. I could even graph it. One, 2, 3, 4, 5. For different values of n, I could graph Sn. 1, 2, 3, 4, 5. Graph these dots. Should you connect the dots? Technically not. Why not? Because the domain is a discrete set, not a continuum. Discrete set. All positive integers, not for example, n equals 1.7 or n equals pi. Why not? Because I say so, seriously. Because that's how sequences are defined. Because it's a useful mode of thinking. Do people connect the dots sometimes? Yeah, but technically you shouldn't. Another thing you can do is you can graph these on a number line. S1 equals 1, S2 equals 2, S3 equals 3, etc. And if you do that, if you graph them on a number line, it's also good to specify the ordering of these, not only with the subscripts, but also maybe with arrows, kind of indicating that you're jumping from S1, jump to S2, jump to S3, jump to S4. It's just a convenient way of imagining things that's got some nice, it's a nice conceptual tool to imagine it that way. All right, let's do another example. Pretty similar. 1, 4, 9, 16, 25, 36, etc. Hey, yeah, perfect squares of whole numbers. Sn equals n squared. N equals 1, 2, 3, 4, etc. Sequences, yes, they can be thought of intuitively as lists of numbers, and we will often do that. Technically speaking, they are functions. If I graph this one, the points would not all be on the same line. They'd be on more of something that looks like a parabola, but again, we would not connect the dots. This is calculus. We should also ask things like, do these sequences have limits or not? And in both of these examples, you would say the limit does not exist. These numbers in these sequences are not approaching any specific number. You'd say the limit as n goes to infinity of Sn does not exist, although in these examples, it doesn't exist in a special way. These numbers are growing arbitrarily large. If you imagine a number line and imagine putting a fence on that number line saying, hey, you can't get past this fence, guess what? Boom, they break through the fence every time, no matter how far to the right you put the fence. They're going to break through that fence. They're going to keep going to the right forever and ever without bound. You could say the limit of Sn as n goes to infinity equals infinity. It wouldn't be a bad thing to write that it equals infinity, though if you do, you should realize it's just shorthand notation to say they break any bound, they keep going to the right forever and ever, and they get past any conceivable upper bound that you might try to put on them. The limit doesn't exist in a special way. It does not mean infinity is the number for us. Here's an example where the limit does exist. 1, 1/8, 1/27, 1/81st. No, not 1/81st, sorry. 1/64, 1/125. That's a sequence. Hope it's pretty clear, whose limit as n goes to infinity is 0. The numbers never reach 0, but they get arbitrarily close, kind of like a horizontal asymptote. Commonly will approach the horizontal asymptote arbitrarily close without touching it. I do emphasize this in Calc 1. You can cross horizontal asymptotes. That's allowed. It's just that with many examples, you don't. This got a direct formula as well. Sn equals 1 over n cubed. N equals 1, 2, 3, 4, etc. And it's got a limit, 0. Strange example. Sine of 1, sine of 3, sine of 5, sine of 7, etc. The pattern is clear. Sn equals sine of n for n equals 1, 2, 3, 4, etc. Oh, no, I wrote that wrong, sorry. Sn is sine of, careful, these are odd inputs, I want n to range through all positive integers, 1, 2, 3, 4, etc. But I want the inputs for the sign to be odd numbers. So you got to do a little trick here. 2n minus 1 is the trick that works here to make the inputs odd when n is first 1, then 2, then 3, then 4, etc. If n is 1, 2n minus 1 is 1. If n is 2, 2n minus 1 is 3. If n is 3, 2n minus 1 is 5. If n is 4, 2n minus 1 is 7. Yes, use that formula. Does that have a limit? I hope you would guess the answer is no, it doesn't. It is assumed your calculator is in radian mode unless you said otherwise. Mine is in radian mode. Sine of 1 is not sine of 1 degree. It's sine of 1 radian, which is around 57 degrees. Second coordinate on the unit circle there. It's going to be close to 1. A little less than 1, 0.84. Sine of 3, the next one, 3 is close to pi. 180 degrees. Sine is going to be close to 0, slightly positive. Sine of 5. Go another 114 degrees. You're going to be down in the fourth quadrant. I think sine of 5 is going to be negative. Sine of 7. Back to positive. You're back to the first quadrant, etc. You could write those numbers down if you want. The first one is about 0.84, then 0.14, then negative 0.96, and positive 0.66. Doesn't seem like these numbers are approaching any number specifically. Yeah, the limit does not exist, though proving that would be difficult, seemingly. Limit as n goes to infinity. Does not exist. And you would not write it equals infinity either, because these numbers, sign of numbers is always between negative 1 and 1. And these inputs are whole numbers here, not simple multiples of pi. So you're always going to get like weird numbers here. They're going to be irrational numbers between negative 1 and 1. That's kind of a strange example. If there are direct formulas, there must be indirect formulas. Let's play around with the calculator a little bit to motivate an example. Say we took 1.000001 as S1, say, our starting value. You could also call it an initial condition, or I like using the word seed. We're planting a seed and seeing how it grows or how it changes. I'm going to take this number and square it. What happens? Seems like the last digit doubles, and if you square again, it doubles again. Is that really happening? Not exactly. There's more digits of accuracy that the calculator is not showing you. These last digits are not actually doubling, though they appear to be. There's more digits that are not being shown. But as you continue squaring, continue hitting enter here, you do eventually get to the point where you can see the lack of doubling, like right. I thought it was that one. I got to keep going. There we go. The 256 did not become a 512, became a 512.01, so to speak. There are 4 zeros before the first non-zero digit there after the decimal point in both cases. But now we're seeing more digits that before the calculator was hiding. And we continue to not get doubling of those digits anymore. And it starts growing really fast. So while I kept hitting enter here, I'm generating a sequence, S1, then S2, then S3, then S4, then S5, etc. Eventually, these numbers grow really rapidly. Once I get above 1 or above 2, say, they grow so rapidly within a few iterations, I am into exponential notation, scientific notation, and all of a sudden I'm at overflow. it's really, in the end, a very rapidly growing sequence. Its limit is infinity, you could say, does not exist in that special way. But how can I write that down? Not so easily with the direct formula. It is actually possible, but not so easily. But I can write down an indirect formula. I've got a seed, S1, the first term, also often called an initial condition. And in that context, you'd often label it S sub 0, the 0th term. And then when n is 2 or bigger, you find the next value, Sn, by squaring the previous value. You use this equation for n equals 2, 3, 4, 5, etc., not when n is 1. Because if n were 1, we'd be saying S1 is S0 squared, and we don't have an S0, though we could if we decided to. That's an indirect formula. Can I use an indirect formula, also known as a recursive formula, to find a direct formula? Sometimes you can and sometimes you can't. It depends on the example, how difficult it is. This example is possible because I can just reuse the same idea. Take the previous value and square it. If Sn is Sn minus 1 squared, then Sn minus 1 squared, the assumption is that's Sn minus 2 squared. Multiply those exponents, you get Sn minus 2 to the 4th. Do it again. That's Sn minus 3 squared to the 4th. Multiply the exponents, you get Sn minus 3 to the 8th. Do it again. That's Sn minus 4 squared to the 8th. Multiply the exponents, you get Sn minus 4 to the 16th. These powers, 2, 4, 8, 16, are all powers of 2. They keep doubling. The powers keep doubling. That pattern seems to indicate that in the end, you'd get S1 to what? A power that's a power of 2. 16 is 2 to the 4th power. Since 1 is the same as n minus 1, the power of the 2 here would be n minus 1, because the power of the 2 matches what you subtract from n, just like it did here. 16 is 2 to the 4th. So it seems like if we got a fixed value of S1, the seed, that whole thing is the seed, that's given, that's a constant. That this is a direct formula. And it is for n equals 1, 2, 3, etc., including if n is 1 even. Because if n is 1, you get 2 to the 0 power there, which is 1. S1 to the first power is S1. You get S1, the seed. To Calc 1 with me in last fall, this should feel kind of familiar, like the project we did involving Mathematica, involving NestList and cobweb plot and Newton's method. Yeah, this is all related to that, but a bit more general. For those who weren't with me last fall, we could think of this formula in another way. We could think of this as Sn equals some function of Sn minus 1, f of Sn minus 1, where the function f, as a function of x, say, is x squared, because we keep squaring. And then, in Mathematica, we can use NestList to iterate that function. F of x equals x squared. NestList, the function name, the seed, and the number of iterations will find the sequence. S1, then S2, then S3, then S4, then S5, etc. Look at those powers of 10. Whoa. Oh, even Mathematica gets to the point where it overflows. Look at that. 10 to the what? 820 trillion, 359 billion, 41,429,306 power. You know, the number of atoms in the observable universe is like 10 to the 80th. That's so much bigger than you can imagine. Way beyond what you can imagine. Overflow. It gets worse, actually, if you try putting fractions in here. Don't go out to 100. Mathematica will stall because the fractions, numerators, and denominators will be beyond your imagination in length. If we try a different seed, same function, x squared, but new seed, 0.99999, what happens now? Now they go to 0. And I think you can get overflow toward 0, or it effectively rounds to 0. 10 to the negative 187 power there. I don't know why it's not doing bigger negative powers there. You'd think it could be able to handle it. The limit there exists. It's the same function, the same recursive indirect formula, but different seed produces a different sequence. This sequence converges to 0. Weird things can happen. Hang with me here a few more minutes. If I change my function to x squared minus 1 and choose a seed of 1, what happens? I get a sequence that goes 1, 0, negative 1, 0, negative 1, 0, negative 1, 0, negative 1, etc., forever and ever. It's bouncing around ultimately between 0 and negative 1. Actually, I had dyslexia or something when I looked at this with the first class, and I didn't realize that the 1 only shows up in the first spot. I thought it was bouncing back and forth between 1, 0, and negative 1. If I change the seed slightly to 1.1, effectively in the long run, the same thing happens, though not at first. No limit. The limit does not exist. Though you might also argue there are 2 limits. What? Negative 1 and 0 are like 2 limits for the sequence? You could give that argument that there are 2 limits. Yeah, kind of, but technically the limit doesn't exist. What if the function's x squared minus 0.5? That seems to have a limit when the seed is 1 of about negative 0.366. And yes, if you try using fractions, you don't want to go too far. I went out to 10 iterations here now instead of 30 because the fractions get really big. The numbers themselves, the ratios are small, close to 0, but the numerator and denominator in reduced form are humongous. So it's better to use decimals. Okay? Strange things can happen. Even much stranger than what we're seeing here can happen.